Okay, so let's continue with our next speaker, Patrizia Vitale from Naples, and she will talk about non-commutative U1 gauge theory in a semi-classical limit.
Thank you. Thank you very much for the invitation. I am really happy to be here again after many years, actually. And I'm really happy to get the opportunity of celebrating Harald, whom I know since many, many years. I think we met in Bayerisfeld first, or in Corfu. I don't remember which one. Sorry? Yes, I have it. It is switched on. I'm sorry. Maybe you can sit more in the front if you don't hear me. This is my voice, so I can't do anything with that, okay? So I was saying I know Harald since I think the 90s, probably. And even though I didn't get the occasion of working directly with Harald, we spoke many, many times. He was really inspiring. He has been inspiring for my work. I have often consulted with Harald to have an advice. You even came in Napoli once for a period. Few times. Oh, few times. So I'm happy to be here and happy birthday to Harald. I will speak about an approach well, which has a shadow of non-commutative field theory because it is actually, it deals with Poisson gauge theories. So we consider space-time manifolds which have a non-trivial Poisson bracket, which is to be intended as motivated by being a semi-classical approximation of a fully non-commutative space-time. And we concentrate on Maxwell theory, on electrodynamics. So this is somehow a motivation. This is a short review of non-commutative gauge theory, which most of you are familiar with. Laser is here, yes. So the space-time is replaced by this non-commutative algebra A. M is a one-dimensional module over this non-commutative algebra. It is a complex module. So matter fields are elements of this M. The covariant derivative is defined in this way. So it acts on the module. It represents the derivations of the algebra on the module. And the Faraday tensor, let's say, is defined as the curvature of this connection. The gauge potential is defined through the value of the covariant derivative over the one generator of the module. And the gauge transformations are the unitary automorphisms of the module. So via gauge transformations, this is how the covariant derivative transforms, and this is how the field strength F. So F is covariant, where, well, here I go directly to an example that we know very, very well, where all those objects can be specified. So this is the algebra. Theta is a constant non-commutativity tensor. Then this is F. F is evaluated on derivations of the algebra. The potential transforms as it should as a connection. And what is important, G, the unitaries of this algebra are star exponentials, namely they are series of this kind, where star is the star product which realizes the non-commutativity of this space. So infinitesimally, if I look at these transformations infinitesimally, I get the transformation, the gauge transformation of the potential. This is a star commutator, which goes in the right commutative limit. This is important. And this is the gauge transformation of F, which is just a star commutator. And again, when the non-commutativity goes to 0, this gives the invariant property of F in the U1 gauge theory. But this is an exceptional situation, namely the one of constant non-commutativity. When I say exceptional, I mean that I recover the standard gauge theory, at least classically, when I send theta to 0. In general, this is not the case, namely, we all know that star derivations, namely derivations of a non-commutative algebra with non-constant non-commutativity, do not reduce to standard derivations. And standard derivatives on the other side are not derivations of the star product. So the question that we addressed is, can we modify the definition of gauge fields and gauge transformations in order to make them compatible with spacetime non-commutativity, namely reproduce the correct commutative limit? We have worked on, for example, on linear non-commutativity. Harald has worked on it, on SU2-like non-commutativity, and we know that we are able to find an algebra of star derivations, but of course then these star derivations do not go to the standard derivations, which means that the action, the gauge action that we are able to construct with these star the derivations will not give back the usual gauge theory on some Rn spacetime. So we want to address this question, and the proposal is to investigate, first of all, the semi-classical approximation, where we do have a better control of the geometry. So we start with a Poisson manifold, and we look for a deformation of the definition of gauge field and gauge transformation such that this question can be addressed positively. So in order to do that, let me have a first look at Poisson electrodynamics, which is this semi-classical gauge theory that I want to discuss. Then I have M, my spacetime. Theta is a Poisson by vector field, the object which will generate non-commutativity. And the standard U1 gauge theory has this gauge transformation for A, and gauge transformations commute among themselves. Standard meaning that theta is 0. In the standard case, theta is 0. So the presence of a non-trivial theta should modify this condition here, namely gauge transformations should be a Lie algebra homomorphism. That is to say, they should close with respect to the non-trivial Poisson bracket that I now have on M. A solution was obtained. So first of all, it was obtained in this paper by Blumenhagen, Kuprianov, Lust, and probably I'm forgetting somebody, in the 80s. And it was used, it was found by using a bootstrap procedure based on completing a strong homotopy algebra. Then there is a paper by Kuprianov alone in the 90s, and essentially the idea is based on this paper by Holm and Zwiebach, where they discuss gauge theories in general, not only non-commutative gauge theories, and they say that all gauge theories should be consistently constructed by completing some L infinity algebra where gauge fields, gauge transformations, field strength are elements of this of a graded vector space, and gauge transformations are found by generalized Jacobi identities that you have in this L infinity algebra. So in this paper with Kuprianov, we essentially got an equivalent result without working with L infinity algebra, but somehow postulating a deformation of the gauge transformation and imposing to this matrix here that this relation here is satisfied, and that in the commutative limit, this gamma goes to the identity because theta is 0, so this should recover the standard gauge transformation. Notice that this is not already the case for example, linear non-commutativity, because in that case, gamma is not the identity, but it is something else. Yes? No, it is not. There is a family of matrices. Well, we have found maps between many solutions that we have. We explicitly addressed the problem for linear non-commutativity. So in that case, we somehow have a universal gamma matrix, and all other solutions can be mapped to this one. So essentially, this gamma has to satisfy a nonlinear equation in order for this condition here to be satisfied, and the solution is not unique. Later on, the problem was reformulated, getting the same result. Namely, it was used the fact that A is a, sorry, there's a mistake here. A is a form. So the role of, so T star M, the cotangent bundle, should play a role. So their idea was to look for a symplectic embedding of the Poisson bracket on M into a non-degenerate Poisson bracket on T star M, which projects down to this one. And then they were able to describe this same gauge transformation simply as this Poisson bracket here, where I am using this lambda. And again, in order for this to be a Poisson bracket, given theta a Poisson bracket, you get an equation for gamma, which is exactly the equation that we were obtaining in this perturbative approach. So this is a few years ago, and let's see how standard electrodynamics fits in this picture, and let's see how this symplectic embedding is better formulated as a symplectic realization, which is something which is due to in the 80s, and then Krajnic later, I think in 2010 or something like that. And so everything fits in this geometric picture. Let me just stress that in this previous approach here, with symplectic, with this perturbative approach, or with this symplectic embedding, we didn't have a geometric interpretation for F, for the Faraday tensor. So again, we asked for F to be covariant under this transformation, and we constructed an F. But in the symplectic realization approach, this F is really a geometric object. So let me explain it first in the standard case. Standard case, again, meaning that theta is 0. So we start with this canonical space. Omega 0 locally can be written in this form. So the gauge potential is a section of the cotangent bundle. And lambda is the Liouville form, PDQ, if we are in local coordinates. So if I look at the pullback, I define, let's say, the pullback of lambda. Well, this is not a definition. Actually, you can compute it. Lambda being a tautological one form, the pullback of lambda gives A, because it simply replaces P with A. In PDQ, it replaces P with A, to say it loosely. So I can define F as the pullback of the canonical symplectic form on M. D and the pullback commute, so I get this. A star lambda being A, I get the standard Faraday tensor by taking the pullback of the canonical symplectic form. So this was the inspiring idea. And then we thought, well, but then we can take this as a definition of F. I look for a symplectic form whose inverse embeds the Poisson bracket on M. So I will have a deformed symplectic form, and then I define F as the pullback of this new symplectic form. What are gauge, and I will show this in the next slides. What are gauge transformations? So we are in the U1 case, so gauge parameters are just functions on R4. Then I could consider the Hamiltonian vector field associated with the canonical bracket, lambda 0, and this acquires this form in local coordinates. This generates a one-parameter group of symplectomorphisms which act in this way on the local coordinates of my space-time. So they do not change the basis, namely they are symplectomorphisms which do not modify the structure on M, but they do act on the fibers in this way. So I can use this symplectomorphism to pull back the canonical one form, and I get this object here, meaning that if I compute this quantity, I get the gauge transformation of my gauge potential. And similarly, I can apply this symplectomorphism to, to omega 0. Since F is the pullback of omega 0, the gauge transformed F will be the F acted upon by this symplectomorphism, and I get the invariant object, which we know from standard electrodynamics. So in standard electrodynamics, gauge transformations are symplectomorphisms of the canonical symplectic form. And these are our U1 gauge transformations. So let's go to the non-trivial case. Theta is not 0 now. So this is my cotangent bundle with a Poisson bracket, which is non-degenerate, and it is such that its projection on M gives me theta, the Poisson tensor on M. Gauge fields, again, they are sections of this cotangent bundle, and the Faraday tensor now it is defined as the pullback of this of omega being the symplectic form which is related with lambda. The lambda is non-degenerate. Okay, so now I can repeat the construction. YF is the Hamiltonian vector field on M, on the base manifold, which I obtain with the Poisson tensor theta. XF is the Hamiltonian vector field, which I obtain with lambda. I have to pull back F on T star M with the projection. And these fields are pi related, meaning that XF projects onto YF. If theta is 0, XF is simply, its projection is 0, as it should. So this is the picture now, because I want to understand what are gauge transformations, and I have to read them from the transformation of the section. So here I was not able to complete the picture, but here there should be A, the section A from M to T star M. Here there is the section ATF. I can draw it on the blackboard. But it's just a picture, so I think everybody sees it. I have T star M. Here I have I and I have M, and this is A, section A. Here I have T star M. Up here I have my TTF. Here I have pi. Here I have M. This is my ATF, which I want to read from the composition of these maps here. So this one is a Poisson morphism. This one is a symplectomorphism. And then you can read the transformation of the section by composing. I think there should be a minus here, minus T here, because I go this way. So this one is a minus. And switch off the light myself. Which one? Both of them? Okay, so I have this one parameter family of sections, this ATF, and I want to look at the infinitesimal transformation. And the infinitesimal transformation is obtained in this way. You can compute it explicitly, and it is a difference between these two fields. A star of YF is a field which lives up. So the whole thing can be written explicitly, and it is an object of this kind. So here you recognize the gauge transformation that we obtained in this way. It's exactly the same. And now, what is F? Well, now F, what is the gauge transformation of F? It's simply the F. So here I have a one parameter family of Faraday tensors, which are obtained by pulling back the symplectic form with this transformed section ATF that I have here. And you can compute it explicitly. And what you get here, again, I think it is C bar minus T. I forgot a minus because I used the expression before. And what I get is that the variation of F is really a derivative with respect to the Poisson morphism on M, which I associate with the gauge parameter. Yes? Mm-hmm. Yeah, that was the way we were computing it. In the approximation, in the first approach that we had to the problem. But let me point out that this gamma here is a function of x and a. Gamma is a function of x and a, and theta is a function of x. So here there is an a. So this means in particular that f contains powers of a. as in non-abelian gauge theories. So this U1 electrodynamics is non-linear. Okay, so, and the important thing is that we recover the Moyal case, which we know and we have control on it, because in the Moyal case, gamma is a delta. So this gamma here is a delta, and we just get the usual gauge transformation of A for the Moyal case. And here, what happens to F? Again, well, F becomes covariant, so it is just a bracket of the gauge parameter F with the field strength F. Sorry for this FF. But it is a generalization, it is a non-trivial generalization, and it is not the direction that we were investigating, for example, for the SU2 case, for the Kappa-Minkowski case, because of the presence of this gamma, which is here. Okay, so let me say a little bit more about symplectic realizations, because I have been using it in the previous slide without saying. So a symplectic realization, according to Einstein and all those people that I mentioned, is there S omega. So S is essentially T star M if we are able to have a complete symplectic realization. Otherwise, we are just in a sub manifold of T star M. Omega is a symplectic to form which projects down to theta. And how do we construct the objects that I have been speaking about previously? So we consider this vector field with theta, which is a Poisson spray, namely it is constructed, so the definition is this one, but I forgot to write, okay, here. So, for example, if I put here the canonical one form, then what I get for the spray is P ddx. This would be the Poisson spray in the case of the T being replaced by the Liouville one form. So this is what is intended by a symplectic realization, namely I use the flow of this vector field here, v theta, this phi theta is the flow of phi theta, to modify the canonical symplectic form to this new symplectic form. In this way, I embed my non-trivial theta into this cotangent bundle, essentially, S. Okay, phi theta is the flow, and lambda, the lambda that we have been speaking about till now is just the inverse of this symplectic form here. In a local chart, okay, here I just write explicitly what is the situation, so I can always find the Darboux coordinates, so the new omega will have this canonical form, but my new coordinate y is obtained by composing the old coordinates with the flow of the spray. This matrix here, epsilon, is invertible and formally invertible, and its inverse is the gamma matrix that I have been talking about before. So this is the omega that I should use to obtain F. So locally, I take this omega here, I consider the pullback of omega, and I have an explicit expression of F in local coordinates. Let's see what this expression tells us. So when we are in the theta equals 0 case, this epsilon here is a delta, and this object disappears, so I get a standard F. When theta is constant, this is a delta. Again, this stays, but it is just a bracket of A with A, and it is the Faraday tensor that we use in the Moyal case, but in general, it is a deformation. As I said, we have solutions for the linear Poisson bracket, so we have explicit expressions for F. Okay, how much time do I have, Harold? Okay, so finally, what are gauge transformations? Well, I can interpret gauge transformations as the action of Lie algebroids on the sections of my symplectic realization, which are the gauge potentials. So which Lie algebroid? Well, T star M has the structure of a Lie algebroid. So T star M plays the role of the symplectic realization on one side, where the sections are the gauge fields, and also as the Lie algebroid whose action, that I will define now, implements gauge transformations of sections of the symplectic realization. The structure of T star M as a Lie algebroid is here. So A, the anchor map, is simply the association of vector fields with forms. In this way, I use the bracket on M, and I get a vector field. And the Lie bracket is just this bracket here. It is either the Kosul bracket, or it has many other names. You see this L A of A is the Lie derivative with respect to this vector field here of the one form beta, of the section beta. Same here, and this is the usual diff. So this is the Lie bracket. It is a Lie bracket when theta is a Poisson tensor. This is known. How does the Lie algebroid act? So this is my Lie algebroid. This is my symplectic realization as a manifold. They are the same object. This is M. The symplectic realization, so phi is the symplectic realization. Essentially, we were calling it pi in the previous pictures, but here I want to use different names. This is definition of the action. And we want to identify this action with the gauge transformation that we have seen. So what is the identification? Remember that this action associates with sections of the Lie algebroid, namely forms, vector fields on the symplectic realization. Which sections in particular? Sorry, here is /mathcal A. Well, here I say a few words about local and global issues of my symplectic realization, but I think we can ignore for the moment when the symplectic realization is complete. Important thing is here, what is this action? So I take a particular family of sections of the algebroid. I take closed sections, which are locally exact, and with these closed sections, I associate this object, which is the Hamiltonian vector field, which I associate with lambda to F. So this is the action. This is the action of the Lie algebroid. The gauge transformation is associated with closed sections. Well, here I just comment on the fact that while we were working infinitesimally with these people here, so we were looking at the Lie algebroid, Kuprianov, Sharapov, and Szabo took a related approach. Their paper came out before our paper, and they started directly from the symplectic groupoid, and then you can connect the two pictures. In which way they are connected? The exponential of the action of the algebroid that I am describing here forms a group. This is the group of bisections of the symplectic groupoid. And these kind of sections are called Lagrangian bisections. So F, which I defined as the pullback through the section of the symplectic realization of my omega, is interpreted as a curvature, and it measures the deviation from this map being a Lagrangian submanifold. Okay, and I think I'm done. Conclusion and perspective. So as a summary, what we call Poisson electrodynamics is an attempt of reconciling noncommutative spacetime and gauge theories. Here, noncommutative is to be intended in this semi-classical approach. The gauge potentials are sections of a symplectic realization of our spacetime M. Lie groupoids and the algebroids, I didn't speak at all about Lie groupoids, but they are the objects which integrate Lie algebroids. They provide the geometric framework where to understand the gauge transformations, which were previously derived via the cell infinity approach. And the gauge transformations are associated with an action of the Lie algebroid, which can be integrated to an action of the corresponding symplectic groupoid. Probably the one of the most interesting aspects is now the geometric status of F, which is the pullback of this symplectic form, which realizes the symplectic realization via a section A. And this meaning a possibility is to interpret it as a measure of the deviation of A. So A is a section in my star M of A from being a Lagrangian submanifold. What are we working on? Understand the relation now between this groupoids approach with L infinity algebras, because in the previous approach with L infinity algebras, F, at least in the version that I have seen, F was not, didn't have a precise meaning. So the F that we obtained and other people obtained in that picture is slightly different from the F that you obtain with this pullback here. Then the other problem is how to introduce matter fields in this picture. We have some ideas. I know that Richard and collaborators, they just considered a particle, a charged particle in this picture. So not really a matter field, just a charged particle. Then the big goal would be to generalize to non-abelian gauge theory. So where to put the non-abelianity in this picture. And finally go to the full non-commutative regime. Here we have some ideas mainly related to the cell infinity picture. Maybe we will talk in next Harald birthday about our results. And this is it. And happy birthday, Harald. Thank you.